All right, so here's our example for gravitational potential energy. So we have an asteroid headed directly toward Earth, has a speed of 12 kilometers per second relative to the planet when the asteroid is 10 Earth radii from the Earth's center. Neglecting the effects of Earth's atmosphere on the asteroid, find the asteroid's speed v final when it reaches Earth's surface. So here I've written down my givens already. We're given an initial velocity of 12,000 meters per second, because it's 12 kilometers per second. Initial R distance is 10 Earth radii, so I just made that 10 R. Final R distance is just R because it's at the Earth's surface. We have V final equals question mark because that's what we're solving for. And I also wrote down our constants. So we have the gravitational constant, the mass of the Earth, and the radius of the Earth. So what we're going to do here is we're going to use conservation of energy, except now instead of mgh for our gravitational potential energy, we have a new equation for gravitational potential energy. So I have energy initial equals energy final. This is potential energy initial plus kinetic energy initial equals potential energy final plus kinetic energy final. And then plugging in those formulas, we get negative g mm over r initial plus 1/2 mv initial squared equals negative g mm over r final plus 1/2 mv final squared. All right, the little m in this case is the mass of the asteroid, so that little mass all cancels out from everything. And then we can just start simplifying here. Now I'm going to insert for R initial and R final my 10R and R. So I get a negative gm over 10R plus 1/2 v initial squared equals negative gm over R plus 1/2 v final squared. And then now I'm going to add that negative gm over r to both sides and combine it with the negative gm over 10r. But first I need to make a common denominator. So I end up getting negative gm over 10r plus 10gm over 10r plus 1/2 v initial squared equals 1/2 v final squared. So here we get a 9gm divided by 10r plus 1/2 v initial squared plus 1/2 v final squared. I'm going to multiply everything by 2 in order to get rid of those 1/2s. So we get 18gm over 10r plus v initial squared, oops, not plus v final squared, sorry, equals v final squared. And then now just reduce that other number, divide both by 2, we get 9gm over 5r plus v initial squared equals v final squared. All right, now we can start plugging in our numbers. So we get v final squared equals 9 times 6.67 times 10 to the negative 11th times m, which is 5.98 times 10 to the 24th kilograms, it's the mass of the Earth, divided by 5 times the radius of the Earth, 6.37 times 10 to the 6th. And then we're going to add the initial 12,000 meters per second squared. So here, we get 9 times 6.67 times 10 to the negative 11th times 5.98 times 10 to the 24th. And then I'm going to divide that number by 5 times 6.37 times 10 to the 6. And then I'm going to add 12,000 squared. And then so I get v final squared equals a really big number, and I'm going to take the square root of both sides in order to get the final answer, which is v final is equal to 16,022.15 meters per second. But let's put it in the same form that we had before. If we divide this by 1,000, we get that v final is about 16 kilometers per second for our final answer.